12:01, so we're 1 minute late. But thanks for returning. For those of us who want to attend the workshop at 2 o'clock, it starts now. It's hosted by Jan-Willem van den Brandhoff and called Speed Reading, something that might come in handy for the next few years. If not, you're to stay here. And we will listen to 2 presentations plus a performance. The 2 presentations until tea break are given by 2 specialists in their field, 2 eminent specialists in their field even. And they will talk about the physical and the psychological approach to time. We have invited Robbert Dijkgraaf, and I should say distinguished university professor
at the University of Amsterdam, specializing in mathematical physics.
And he will take us back to the days of Big Bang. That's the first. The second presentation will be given by Joke Hermsen. She's a philosopher, but also a literary novelist. And she recently, in 2009, published a book which was called, in Dutch, Stil de Tijd, translated into Time on Our Side. This book actually has been an enormous commercial success, as far as I understood from the website. 9 reprints in 1 year for a non-fiction book is unbelievably big. So that's an achievement in itself. In between these 2 presentations, we will welcome Alexis de Rode, a poet, Dutch poet, who will read a few poems that he recently wrote. They are on time, and he will read them both in Dutch and in English. After that, Alexis will also give a workshop at 3:30 p.m. On speed and on time and writing. But first, Robbert Dijkgraaf, already told you, who will show us how the notion of time came into being, where it actually began, and probably where it might end. And of course, for us designers, it's interesting to know what we should know about time when we try to think of products that have anything to do with time and the spread of time. I would like to invite Mr. Robbert Dijkgraaf to do his presentation.
Well, thank you and good afternoon. It's a great pleasure and an honor to speak to you, particularly here at the beginning of a new year, after what has been for many of you, I guess, a hard reset, and actually to talk to you about the beginning of time. Now, time has many different aspects, and I'm a scientist, so I feel a little bit like I'm on a very highbrow conference on various applications of wood, and I'm a carpenter. Time is the thing that I study every day. I write equations, and there is a symbol T, which is time, and I work with it. And in some sense, I think as a physicist, I've learned time from a very different angle. And I want to share some of these experiences with you. And I think time is also a wonderful organizing principle in the sciences. So it's not only are we living it, but it's at the same time something that brings together various aspects of science, of philosophy, and also has very different aspects that I think might be new for you here. So one thing, of course, I will have to talk about is to talk about experiences that are very far removed from everyday experience. The wonderful thing is that science, we have by microscopes and telescopes, we have learned to look at the very small and the very large. And the amazing thing is that we can actually understand these. Einstein has said, the most amazing property of the universe, it's understandable, because we with our brains they have been evolving, living in the jungle and doing all kind of everyday things, while we are able to understand an elementary particle or the universe itself. I think is a great miracle. It shows something that everything is hanging together in a very coherent way. Now, particularly I want to talk to you about 2 realms that are very far removed from your experience. They will probably stay very far removed, but they're part of the universe that you are living in. So that's why I want to share them with you. And this is the world of the very small particles and the world of the very large, cosmology. And what do we learn from the physical theories that describe that? Quantum theory and relativity theory. And one of the things that we learn is that we have a different way at looking at time. If you go back a few hundred years, time was like a gigantic clock. Newton said, it's mathematical time, it's true, absolute and mathematical time. It flows of itself and by its own nature. So he had this image as a big clock somewhere above the universe, and it's ticking, and we are like a machine, a clockwork working according to the metron set by that clock. And also space. Space was considered to be, basically it's infinite, it's rigid, it's huge, it's invariant, it cannot flex, it cannot shape. It's like a stage that is permanent, on which you and I and the particles are basically playing their act. So there's this whole idea of the universe as a big clockwork, and essentially what science is predicting, if we know what the situation is right now, what it will be a minute later, 2 minutes later, a year later, hundreds of millions of years later. And that's in some sense what time is for us. It's basically a machine, it's kind of the oil on which this big machine runs. Now all of this changed completely the last 100 years. And I want to share some of these new insights with you. And of course they all go down to this man, Einstein, who in 1905 made this remarkable statement that time and space should belong together. And he said time is the fourth dimension. So this is already a point that basically everybody decouples from physics. But actually now I have you hostage. So I will actually try to explain this to you. So who's afraid of extra dimensions? And you as a designer should not be. And there's a very nice way to explain this. And this goes back actually to the time that geometry was developed, this higher dimensional geometry, in the 19th century. There's a famous book called Flatland. You might have heard about it. Flatland is a book that was written in the Victorian times in England by a school teacher, and it describes a world that's completely flat, that has only 2 dimensions. And in that 2-dimensional world, creatures live. And in fact, if you read the book, you learn much more about England than you actually learn about geometry, because it's a strict hierarchical society. So for instance, most people are little triangles. These are kind of the workers, there are many of them. And then you have like the school teachers, they are squares, and so it goes on. If you're a polygon with many angles, then actually you're very high in society. And in fact, the highest one are the priests, they are circles. The infinite many angles. And of course, and here is the kind of politically incorrect, there are also 2-dimensional objects, the 2 gons, there are like little line segments that you see over there, really tiny, and they are the lowest level of society, and these are the women. And in fact, the writer of this book has great pleasure in working this out. So for instance, he has these descriptions of houses, there's a big door where the man of the family can enter, and it's a small door where the women can enter, and then he goes on with the bedrooms and everything. It's really... But this land, this flat land, is sometimes perturbed by something amazing. Something enters the room, neither through the men's door or the woman's door. It just materializes inside, and then it disappears again. And it leaves the inhabitants of Flatland completely bewildered. And you can already guess what's happening. Of course, something is entering from the 3rd dimension. In fact, it's going up. And it's called the sphere, and then slowly the people of Flatland are discovering there's a 3rd dimension. And so they're a little bit like ants. Ants also are living basically in a 2-dimensional world and don't see that there's also height. Now, if you are a mathematician, you are not afraid of extra dimensions. In fact, you could think of a cube in every dimension. A cube, we usually think of it as a 3-dimensional object, but you could have it in 1 dimension. In 2 dimensions would be a little line segment there on the bottom of the screen. In 2 dimensions, it would be a square. In 3 dimensions, you all know, it's a cube. And then you can go on. So for instance, in 4 dimensions, there's something called a hypercube that lives, and you can construct it and you can study it. And within mathematics, it's perfectly alive. And in fact, you can try to visualize it. Now, for instance, I've tried some tricks. So this is a visualization of a 2-dimensional cube, just a square. Now, it's very easy to show this. But here's something 3-dimensional. Now, actually, of course, this is a visual illusion. you're not looking at an actual three-dimensional object, you're just looking at the projection on the screen. But in fact, even if I would have constructed the three-dimensional cube, brought it all the way from Amsterdam here and turned it around, you would say, oh, that's truly three-dimensional, but still you're watching the backs of your eye, you're looking at your retina. So the third dimension you never really see. The only way you construct it is in your mind. And so why isn't it possible to see the fourth dimension? Now I had a colleague who said, I can do this, I can project a four-dimensional object into 3 dimensions, just as I here projected a 3-dimensional object on a 2-dimensional screen. So let me show a hypercube. So you look something like this. I think this is a very bizarre object. And I had a colleague, so it is even better if you use a stereoscope. And my colleague, he looked for a full year at these images, hoping that something would say click in his brain. It did not. I think very brave experiment. It reminded me of the experiments, where you flip the image. This is famous, where everything is upside down, and if you do that after a few hours, then it's back again in the usual orientation. Of course, if you remove your glasses, you have to be lucky or hope that it flips back. It does in that case, but so here, what happens to you if you see the fourth dimension? So I don't know if there are any volunteers, but clearly you need more than 1 year to look at these pictures. But you can try to visualize. For instance, you can make a model. For instance, you can make a cube out of a piece of paper. You just cut it out and tape it together. So can't you make like a 3-dimensional puzzle that you tape together? Well, you could do this like this. If you somehow are able to glue all these ends together, you get this 4-dimensional cube. And the many artists actually in the 20th century were fascinated by this. You see them everywhere. Particularly, this is Dali, but if you go in the 1900s and 1910s, many artists try to depict this fourth dimension, and I must say not very successful. But there's another way to understand this, and this is use time, which is the topic of today. So I want you to think of a movie, a film roll. So I have a very simple movie. So we look at this movie over here. So what we see is 2 little balls dancing around. Now think of the individual images by which this movie is made. And so these are all individual images, and now think of them as pictures and put them on a stack, as you do with your holiday pictures. So here on the left you see the pictures. And you see, the higher you are in the stack, later in time. The first image, first in time, is on the bottom, the last is on top. So now we see we can make a 3-dimensional pile, and the height is time. Now what Einstein said, just magically glue all these pictures together and make one big, in this case 3, but in reality 4-dimensional piece of object, which is over here. You see the 2 balls now have become these kind of spaghetti strands, a green one and a red one. Physicists call them world lines. You are also a world line at this moment. You don't realize it, but you're going into time, 1 second a second. So you're forming these kind of these figures here in space-time. So space and time belong together, and that's the object that physicists study. And for a physicist, space is not important, time is not important. What's most important is one point in this space-time. So what's this? Well, for instance, this is such a point. A moment in time in a position in space. And these are like the little grains of sand that build up space-time. We call them events. And your life is a whole chain of events that forms this world line that goes through space and time. Now the amazing thing is that this space-time, in some sense, is there for physicists, is there just there. No, it's not happening. It's like I give you the DVD of a movie. You have the whole movie. You cannot really live it. You cannot be touched by it. No, it's not exciting or whatever, funny. But because you have to see the movie image by image. So in some sense, we are a little bit unfortunate that we always have to go picture by picture through this stack. But if I'm a physicist, I study this whole thing at once. The whole history at once, from the beginning to the end. And what you can do, you can say, well, let's take now. Then I take a slice. I basically take a big knife, and I slice this space-time in the middle, and this is now. But Einstein said you can slice it in different ways. So somebody can take another knife and slice it like this. Which is very strange. Because think of your holiday pictures. If I would do this, then this part here would be a picture at the beginning of the week, and here you would have something of the end of the week. So these are things which are not happening for one person, are not happening at the same time, but here they are happening at the same time. So these ideas were so crazy that people had a great difficulty to accept this. In fact, most of them, when Einstein first came with ideas, they did not accept. They basically, to say it very impolitely, died out. There was a new generation, in some sense, that took this as their starting point. And there's a famous discussion where Einstein talked to a very grand old professor, and he said, what is the mechanics on which this is based? So that's, how do you derive all this? And Einstein said, no mechanics. No, I'm not deriving this from anything. This is my starting point. And it's a very productive starting point. Right now, it's the canonical way in which we look at space and time. And actually it goes further, because I said already we have this stage, but Einstein showed that space and time are one material, and this is not a rigid material, this is a flexible material, a material that you can bend and curve. Space itself can be bent and curved, and it can be bent and curved if you put matter in it. So for instance, the moment you are standing in space, it's not very noticeable, you will bend the space around you, and that effect is called gravity. So that's actually a very interesting aspect, because that means that space and time, which always was something like a background on which things are happening, right now it's an active player in the big theater of physics. So space and time themselves can move, they can act, they can change, they can curve, and so it's really a material as you would take a material as plastic or wood. So when Einstein had derived all this, he was the first one that could ask the following question: take the universe and see how it will start to behave. So he could do a computation. It was really, I think, the most remarkable thing that a living person can do. See what is the history of the universe. So he started to compute with the universe, and he found an amazing discovery that the universe was expanding. Just the space itself was like a balloon that you blow up, was growing and growing and growing. And this has tremendous effect, because now we could also say, what happens if I go back in time? Well, if the universe is expanding in the future, it will actually collapse in the past. And he found there is a moment in time where the universe basically is all squeezed together in a single point. That's the thing that we now call the Big Bang. The Big Bang only got its name in the 1960s, when some physicists thought this is a completely ridiculous idea. So I give your theory a ridiculous name. Big Bang. Haha, who believes this? But now actually people carry it with great pride. And there are big bangs, and there are big crunches, and big rips, and big breaks. There are all kind of big things in describing the cosmology of our universe. Now, you should remark that at that time, the fact that time had a beginning, you might say it's very obvious, because didn't we always have creation stories? Well, for a long time, people were very seriously believing that the universe was created on the 23rd of October, the year 4004 BC. It was a long debate among scientists, was this in the morning or the afternoon? So it was first computed, you all know probably the story, by an Irish archbishop, Ussher, who actually took the Bible and all the pieces in the Bible and pieced together this date. But he didn't say whether it was the morning or the afternoon. But people came after him, they argued it was at 9 in the morning. So God was an early riser. But actually this was, in some sense, long behind us when we came in the area of Einstein. At that time, all the scientists believed that the universe was basically always there. In some sense, really like an empty piece of paper that's always there on which you can put various things. Nobody actually was taking seriously that time itself could have a beginning. So this was really an amazing idea. And it took a long time for people were convinced. And actually, as always in physics, you get convinced when you see the data. And the first data were measured by these two engineers. They were engineers living in the United States. And they get a task to get a little buzz out of this big radio telescope. So there was a radio telescope used for communication, a microwave communication, and just there was a little hiss in it, and they tried everything. If you read their paper, they see that they actually thought that was pigeon poop that was in there, but it was not. They removed this, and still there was this little bzzz. And then they met the physicists and said, well, maybe you're picking up a signal from the universe, which dates from the very, very beginning, actually a few 100,000 years after the Big Bang. And this turned to be correct. In fact, what you can do, you can take your television at home, unplug it, must do that perhaps anyhow, and just watch on the static on your screen. Then 1% of the static is actually coming from little photons, light particles, traveling 13.7 billion years all the way through the universe to your television screen and turn a black dot white. And so you can pick this up. In fact, I've seen a nice student project the other day who actually did this measurement very carefully. So it's around here, but we can study it now much more precisely. In fact, now we have big satellites that listen, in some sense, to the earliest sounds coming out of the universe. And what they show is not just this static screen, but much more detailed. This is how the universe looked at the very, very beginning, 13.7 billion years ago, 400,000 years after the Big Bang. And as many people pointed out, that actually it's like it looked like an impressionistic painting, but it's actually designed, because if you see here, there's the initials SH from Stephen Hawking. They're over here. It's quite remarkable. It's with pure chance, this, but once you see it, you cannot unsee it. No, it's so every time I see this, I see immediately SH. And but perhaps you see your own initials here. But of course, that's just a joke. Actually, what we can do now is that we can basically reconstruct the whole history of the universe, starting from this very, very earliest moment. So here you see it animated, like in half a minute. You see that these small variations, they are attracting clouds of dust and matter. They light up. These are the very earliest galaxies. Then the galaxies start glowing. They will form many stars. The stars start orbiting around the interior of the galaxies. Planets form. In the end, our sun, our planets, and then finally we have the whole universe as it's lying in front of us, starting from this very, very, very modest beginning to life on Earth as we know it now. So this is an immense history, and not only it's amazing, I can show it in 30 seconds, but the fact that within basically 100 years, we have completely reconstructed the history of our universe. You know, and there's only one universe in which we are living, so I think it's a pretty amazing achievement. And so we really can see basically all the different stages of life in the universe we understand. And the only problems are if we go back to this very, very beginning. Because you can see here's our picture, and then there's this kind of thing that says quantum fluctuations, which is the very beginning. So the question that anybody asks, any physicist, you know, how can time begin? You know, what was there before the Big Bang? Is really a very, very deep question. And to answer that question, I think that's a beautiful, I would say almost poetic aspect of our universe. At that time, the universe was so small, it was really more like an atom or a particle than a universe. So to study it, we actually have to study the laws of the very small. And they are completely different. So tell me, now I will tell you something about the world of the quantum world. That's the world of particles and atoms. Now, I begin with a question that you might have, everybody of you're familiar that our world is made out of atoms. And you read about them in your school books. But you see, it's quite amazing that if you have these elementary particles, they are actually exactly the same. If you have two electrons, they have the same weight, you know, not one a little bit bigger. So you might imagine if there's the cosmic designer that's making electrons, he has a factory that's actually working very precisely. No? They're all exactly the same. How can this be? This is a question that physicists have struggled with for a very long time. If you might make a factory that makes ping pong balls, and they're all exactly the same, that's really remarkable. Could be a little dent in one, a little scratch on the other. There's never a scratch on an electron. They're perfect. Why? Well, the origin of that theory goes back to a telephone call between two famous physicists, John Wheeler, who was the advisor of a brilliant student, Richard Feynman. And Feynman became a kind of a cult hero, so you might have heard about him. And Wheeler called Feynman in the middle of the night. He says, I've been thinking about this question why all the electrons are the same. And I have the answer. There's only one electron in the whole universe. Now, I don't know if your students here, if your advisor calls you in the middle of the night with a funny story, you should be wondering, was he drinking or something? No, he wasn't drinking. But he had a really crazy idea. So let me tell you about this crazy idea, because I like it so much. So this was Wheeler's idea. So this is again this stack of pictures, the space-time. So think of your holiday pictures, And now we're describing this one electron. And if nothing would happen, it would go up, up, up. Every second, another second up in the picture, like we are going up. Time is flowing, we can't stop it. But suppose, Wheeler said, suppose you could back in time. Suppose you could go up and down again. That would be nice. For instance, I could go down in time, back in time, come up here on the stage again. And there would be two of me. And you know what? We would be very similar. In fact, we would be identical. And then one of us goes back again, and there would be a third one. There are three of us. So suppose this is possible. This was his picture, though. This electron goes up and down and up and down and up and down, and makes this enormous big knot. Instead of a strand that only goes up, it's now a big knot. Now suppose you take a picture. So the first picture here, there's only one. But suppose I take a picture a moment later. I cut this big knot, and there are many, many strands sticking out. But just if you cut a big knot of wool, of course, all these little strands have the same color because they're made out of one string. So here you see many particles. So all of these particles are identical because they're basically time-traveled copies of themselves. Now, this is a kind of a crazy idea, but actually Feynman, the student, took it further. And there's a beautiful, I find this a very interesting picture. This is a page from his sketchbook a few years later, when he was trying to make this ridiculous, crazy idea work. So here you see him carefully sending the particles on his notebook back in time, and he's computing what happens. What happens if I send the particle back? And he made a wonderful discovery. You actually noticed that the particle going back in time is the same as another particle, the so-called antiparticle, going straight up in time. So he said actually this makes sense in physics. Particles can go back in time. And he invented a language to compute this. And you see, everybody at that time was making huge computations. But Feynman was making pictures. And like this, they're called Feynman pictures. And these were very powerful. So for instance, there's a famous incident where he came to a huge meeting, and one of his colleagues came and, well, did you hear? Somebody has been doing computations for several months, and he has this result. Can you do that? And Feynman took a sketchbook, made a picture, and with 1 minute said, yes, I have the same result. And he said, and then he showed him the result. And then his colleague said, but what is this thing here? Well, it's like a dial. I have not have one result, I have a whole series of results. They said, it's not possible. This guy took 3 months to compute one, and you compute them all with a drawing. And Feynman, in fact, in his one letter, he says, wouldn't it be nice at some point if all the physics books would be full of these drawings? And now they are. In fact, there's a nice incident that once a physics student was walking in Los Angeles, and then he saw a van. And the van had all these kind of diagrams on it. So a lady was driving the van, and he stops the van, and he says, oh, madam, do you know that I'm a physicist, do you know that these pictures on your van, they are Feynman diagrams? And she said, yes, I know, I'm Mrs. Feynman. So actually, going from a crazy phone call in the to a van driving proudly in LA is really a big step. So this is the way in which now we think physics works. And it's really crazy theory. So for instance, particles can go up, but they can do funny things. For instance, they can split up in 2 particles or 3. They make all these funny diagrams. And the most amazing thing they can do is this diagram over here that I will show you. Because, and I'm not joking, I think if you see what is the line of argument, is that the time and space, being the background for all phenomena, became part of the show, so to say, with Einstein. But now I would say they're right in front. They're the main character in physics. So understanding nothing, empty space, is really I would say, the biggest challenge in physics. And I don't think I should write a grant proposal that please give me a few millions to understand nothing, but actually, of course we don't write it like this, but we are serious. Because the following thing can happen. This can happen. So what is this picture? Well, think of this. This is a particle going up in time and then going back again. And up and back, and up and back. Out of nothing. This can happen. In fact, it not only can happen, it must happen, and it happens right now here in this room. There are millions and billions of particles just appearing for a short time and then disappearing again. This is a fact. It can be measured. In fact, it was measured by the Dutch physicist Casimir, right here in Eindhoven. And it has a tremendous effect because empty space, this is my own little PowerPoint exercise to visualize my picture of empty space. So I think of it as a boiling pot. Permanently there are little particles that are allowed in this funny world of the small, called quantum theory. They're popping out and they're disappearing again. They're popping out and disappearing again. And so in some sense it's almost like it's a glass of Coke. There's all these little bubbles in it. And that makes actually space and time come alive. It gives it in tremendous energy. And in fact, you can measure this. So the remarkable thing is if you take a piece of empty space, you can study it. And you can study it because there is lots of empty space in the universe. So we can see what is the effect of this space. What it will have, that these little particles here that can only live for a briefest moment in time, they still carry energy. So there is energy in space-time, and Einstein has said anything that carries energy will curve space-time. So by looking very carefully at how space and time are curved, we can see how much energy is there in space-time. And we find something quite remarkable. This is something that has been done the last, say, 5 to 10 years in cosmology, and it's completely shattered our point of view of the universe. Because we have been weighing the universe and seeing how much stuff is there in the universe. Now, there's lots of stuff. Planets, galaxies, stars, nebula, radiation. But if you add it all up, you find that it's only accounting to 4% of the total energy of the universe. Then we have now indications there is other matter, we call it dark matter, which is not lighting up, so it's not it's not what the stars are made of. It's a big cloud surrounding our galaxy. It's very mysterious, but still it's matter. So at sometime we will discover what's made of. And it roughly gives 1/4 of the universe. And then 3/4 of the universe is made out of empty space and time. And that carries 3/4 of the, say 3/4 of the energy is carried by empty space and time. And this has a tremendous effect because what it does, it is like a spring. The empty space is really like a spring. So if you take a piece of foam and I pull it together, it wants to expand. Actually, this energy, we call it dark energy, in empty space and time, is pulling the universe apart. So what we are feeling now, not only is the universe expanding, as Einstein predicted, but it's it's like accelerating. It goes faster and faster and faster. And by going faster, it creates much, much more empty space. And the empty space is helping to accelerate. So you can see this is a rather disastrous scenario. You're creating, in some sense, more of the stuff that's helping to pull you apart. So physicists were very much worried whether there would be the thing called a big rip, which is just that time ends altogether. And of course, you're always worried, is that tomorrow or something, but it could happen. I think now we are safe, but one effect it will have, it will pull everything apart, and it will, in some sense, make us live in a universe which becomes very, very empty. Basically, it will carry all the other galaxies apart, and we will live in kind of an island universe. And I've often felt it's like you buy, well, again, if I take this kind of image of a movie, a film roll, then it's infinitely long, and there's an interesting part in the beginning, we are living through it, say the few 100 billion years, but then it turns black forever. And perhaps I shouldn't repeat it, but it's this very funny line of Woody Allen said, eternity is a long time, particularly at the end. And that's really capturing it perfectly. And there are many, many physicists who really are struggling with this idea. How could the universe be developed and live endlessly wasting basically everything, apart from a tiny, tiny fraction, that's in some sense, relatively speaking, you can ignore, that we are living. So first of all, it means that we're very fortunate. We're just living right in the interesting piece of the universe. But then it just goes on and on and on. And I think that's in some sense what people find very, very confusing. So it could be another end of space and time. So let me share you some other ideas. So now I first have to say something about the phenomena that you might say, well, ending of space, ending of time, what you're talking about, this is all kind of theorists speaking, this is on equations. Show me the place in the universe where the space is ending. Now actually, since, again, the last 5-10 years, we can show many of these places in the universe. They're called black holes. Black holes are objects you find everywhere in the universe. Particularly, you find them in the middle of a galaxy. So again, we are our sun is a little star. It's somewhere out here in our galaxy. There are hundreds of billions of these galaxies in our part of the universe. And right in the middle of the universe, we find there is an enormously heavy object. And for instance, if you look at the heart of our galaxy, with a telescope, you see these beautiful pictures. But if you even look closer, you see stars. And these are a kind of a movie, it's speeded up, of how the stars are moving the last 15 years. And you see that there is an area where some of the stars are really moving fast. They're orbiting something. And now we know what it is. There's a huge galaxy there, a huge black hole, roughly 3 million times as heavy as our sun. So it might be something that has eaten up millions and millions of sun, or perhaps it was created for the very, very beginning. That's there. And in fact, all the galaxies we know have these huge black holes. Here's a very spectacular case, because you see these things shooting out left and right. Hundreds and thousands of light years big, are shooting out this little point in the middle. So they tremendous explosions there that really, you cannot really exaggerate them. And we also know in some sense what's happening there. So when a star basically ends its life, it collapses together and the gravity pulls it back all the way to a point. In fact, to a point in the middle, which we call a singularity. If you actually enter this point in the middle here, then you're doomed. You're completely ripped apart. Luckily, there's a region around it called the horizon. It's a kind of safe haven. If you don't cross that horizon, you're fine. But once you cross in the horizon, you're doomed. Now, then I often have discussions with my physics students. You say, well, why am I doomed? If I just have an enormous rocket, I will pull out. But you're doomed in a very strict way. Because I said always in these pictures, time is flowing upward like this. But within a black hole, time is flowing inward. Now, if I'm standing here, and I see there's like 1 meter to go, and then I start walking here, I say, at some point my course of action will end. You say, yes, I'm convinced of that, I will just hit this wall. In the same way, there's inside the black hole, there's a wall that you can hit. So inside the black hole, time ends. Physicists are struggling to understand this, but I could say some words about it. Let me just skip this. There are some ways to quantum mechanics might come to a rescue. But the thing is that if we look now in the universe, we see many, many places where time is actually ending. Little pieces of time. Like the time inside that black hole. For us, outside, time goes on. So already little parts of it are stopping. And in fact, this could be part of our own very distant future. In the end, our whole galaxy can be one big black hole and we can be sucked in and that's it. Now, this is a very gloomy scenario, the end of time. So there is a way out. And let me say 1 or 2 words and then I'll stop. How physicists think that there could be a way out. Well, they describe something they call the cosmic landscape. And the cosmic landscape is something that is in some sense describing all the possible worlds that can exist. So for instance, we have a world that's made out of particles or atoms or laws of nature. People like me study these. But you could say, well, why not make a different world? Again, take this picture of the cosmic designer. Create all possible worlds. A world where there are no electrons, but another funny particle or something. And suppose that so in some sense you think of this landscape as the world, all possible worlds that are there. And we are just a little ball that's lying here, so we are living in this little valley here. Could we escape to another world? And we're not saying another world in space, but really a completely different world with different laws, perhaps even different logic. Now, in principle, you cannot. But the funny laws of quantum mechanics, where certain things can happen, like traveling back in space, in time, which are not allowed for us, allow you what we call quantum tunneling. That is, you can go through the hill to the other side of the hill. This happens, for instance, if a radioactive atom decays. It basically is not allowed, yet it does it. Do it anyhow. So there's a small chance that we could end up in a different universe. But I say very small chance. So you have to wait a long time. But we have all the time we need. We have an eternity. So physicists say at some point this will happen. And then actually in some sense we get a very interesting case. We get something that will what we call a baby universe. Out of our universe a new universe will be born. None of us will go with it. In fact, we couldn't even live there because there are different rules. We would not be allowed in some sense. There's no passport. You can't go with. But space and time will make the next step, and we start all over again. And then they will create another babies. And in fact, you know, we shouldn't be presumptuous. Why would we be the mother? Perhaps we are one of the babies up here. We have been born out of another universe. And all these different universes live there. And then there's something that physicists like to philosophize about, what you call the multiverse, which is a whole collection of universes. Now this is us. This is what we describe. And there are all these other objects. We cannot visit them. We cannot study them. But they could still be there. So I feel that's perhaps a slightly comforting thought. Because we not only will not end our life in the gloom and doom, but we kind of step up to the next level. Unfortunately, we won't be there. But there is somebody living in a new universe, and they will actually study it and discuss the beginning and the end of time, and perhaps this discussion that can go on there. So I think here I'm at the end, at least, of the time that I was allowed. Thank you very much.
Thank you, Robbert. Wonderful and mind-boggling, to say the least.